An infinite loop is a sequence of instructions in a computer program which loops endlessly, either due to the loop having no terminating condition, having one that can never be met, or one that causes the loop to start over. In older operating systems with cooperative multitasking, infinite loops normally caused the entire system to become unresponsive. With the now prevalent preemptive multitasking model, infinite loops usually cause the program to consume all available processor time, but can usually be terminated by the user. Busy wait loops are also sometimes called infinite loops. One possible cause of a computer freezing is an infinite loop. Others include thrashing, deadlock, and access violations. Intended versus unintended looping. Looping is repeating a set of instructions until a specific condition is met. An infinite loop occurs when the condition will never be met, due to some inherent characteristic of the loop. Intentional looping. There are a few situations when this is desired behavior. For example, the games on cartridge-based game consoles typically have no exit condition in their main loop, as there is no operating system for the program to exit to. The loop runs until the console is powered off. Antique punch card reading unit record equipment would literally halt once a card processing task was completed, since there was no need for the hardware to continue operating, until a new stack of program cards were loaded. By contrast, modern interactive computers require that the computer constantly be monitoring for user input or device activity, so at some fundamental level there is an infinite processing idle loop that must continue until the device is turned off or reset. In the Apollo guidance computer, for example, this outer loop was contained in the exit program, and if the computer had absolutely no other work to do, it would loop run a dummy job that would simply turn off the computer activity indicator light. Modern computers also typically do not halt the processor or motherboard circuit driving clocks when they crash. Instead, they fall back to an error condition displaying messages to the operator, and enter an infinite loop waiting for the user to either respond to a prompt to continue, or to reset the device. Unintentional looping. Most often, the term is used for those situations when this is not the intended result. That is, when this is a bug. Such errors are most common among novice programmers, but can be made by experienced programmers as well, because their causes can be quite subtle. One common cause, for example, is that the programmer intends to iterate over a collection of items such as a linked list, executing the loop code once for each item. Improperly formed links can create a reference loop in the list, where one list element links to one that occurred earlier in the list. This joins part of the list into a circle, causing the program to loop forever. While most infinite loops can be found by close inspection of the code, there is no general method to determine whether a given program will ever halt or will run forever. This is the undecidability of the halting problem. Interruption. So long as the system is responsive, infinite loops can often be interrupted by sending a signal to the process, or an interrupt to the processor, causing the current process to be aborted. This can be done in a task manager, in a terminal with the Control-C command, or by using the kill command or system call. However, this does not always work, as the process may not be responding to signals or the processor may be in an uninterruptible state, such as in the Cyrix coma bug. In some cases other signals such as SQL can work, as they do not require the process to be responsive, while in other cases the loop cannot be terminated short of system shutdown. Language support. Infinite loops can be implemented using various control flow constructs. Most commonly, in unstructured programming this is jump back up, while in structured programming this is an indefinite loop set to never end either by omitting the condition or explicitly setting it to true, as while some languages have special constructs for infinite loops, typically by omitting the condition from an indefinite loop. Examples include Ada, Fortran, Go, and Ruby. Examples of intentional infinite loops. The simplest example. The form for an infinite loop is traditional, appearing in the standard reference the C programming language, and is often punningly pronounced forever. This is a loop that will print infinite loop without halting. A similar example in BASIC. A similar example in x86 assembly language. Another example is in DOS. Here the loop is quite obvious, as the last line unconditionally sends execution back to the first. An example in Python. An example in Bash. An example in Perl. Examples of unintentional infinite loops. Mathematical errors equals. Here is one example of an infinite loop in Visual Basic. This creates a situation where x will never be greater than 5, since at the start of the loop code x is given the value of 1, thus, the loop will always end in 2 and the loop will never break. This could be fixed by moving the x equals 1 instruction outside the loop. Essentially what this infinite loop does is to instruct a computer to keep on adding 1 to 1 until 5 is reached. Since 1 plus 1 always equals 2, this will never happen. In some languages, programmer confusion about the mathematical symbols may lead to an unintentional infinite loop. For example, here is a snippet in C. The expected outputs is the number 0 through 9, with an interjected equals 5. Between 5 and 6. However, in the line if above, the programmer has confused the equals with operators. Instead, this will assign the value of 5 to A at this point in the program. Thus, A will never be able to advance to 10, and this loop cannot terminate. Variable handling errors equals. Unexpected behavior in evaluating the terminating condition can also cause this problem. Here is an example. On some systems, this loop will execute 10 times as expected, but on other systems it will never terminate. The problem is that the loop terminating condition tests for exact equality of two floating point values, and the way floating point values are represented in many computers will make this test fail, because they cannot represent the value 1.1 exactly. The same can happen in Python. Because of the likelihood of tests for equality or not equality failing unexpectedly, it is safer to use greater than or less than tests when dealing with floating point values. For example, instead of testing whether x equals 1.1, one might test whether x